Here we are going to find out the potential energy of an electric dipole. It is in a uniform electric field. Here E is the electric field that is uniform, and in this the dipole is taken from infinity away from electric field and put in the electric field in such a way that the direction of the dipole moment of this dipole is in the direction of the electric field. One thing. Second thing, whenever we have done the work done, that is stored in the form of the potential energy within the dipole. So this is what we want to find out. Now the net force on these two charges are having opposite nature and equal in magnitude, so that is 0. But it is clear from the figure that this minus q charge has traveled extra distance, that is the distance between these two dipoles, 2l, in comparison to the plus q charge. So the net work done will be because of this extra distance traveled. We know that work done is equal to the force into distance. So here the force on the charge minus q and the extra distance it has traveled is to be taken in consideration. So W comes out to be, the work done comes out to be equal to the QE, because force is equal to electric field per unit charge. From there, that relation we got this minus QE into 2L. Now Q into 2L is our electric dipole moment denoted by P. So we have got the work done as a product of the electric dipole moment and the electric field. Now the work done that we have calculated is the product of the dipole moment and the electric field. According to the law of conservation of energy, the work done is being stored in the form of potential energy. And from here we mentioned that the work done in the electric dipole is also following the law of conservation of energy, and the potential energy stored in the dipole is given by U naught equal to product of the dipole moment and the electric field. Here the dipole is making an angle 0 degree with respect to the electric field. It is condition mentioned as the stable equilibrium, and the potential energy is denoted by the U naught. Now if the dipole is rotated at an angle theta, the work done is given by, I have taken the direct result. Already I have proved that work done when dipole is rotated at some angle. So putting these values, we have U theta equal to U naught plus the work done. Here it is the potential energy when dipole is rotated at an angle theta, and U naught is the initial stable equilibrium potential energy that we have found out, and this is the additional work done in rotating a dipole. It will be experiencing a torque. Now we found out that there is increase in the potential energy, and that comes out to be equal to the dot product of these two vector quantities. Now if the dipole is rotated at an angle 90 degree, this dipole is at perpendicular to the electric field, then putting the values, since cos 90 is 0, so the potential energy comes out to be 0 in this case. Now we talk about the condition when this dipole is just rotated at an angle 180 degree. Here on putting the value of the theta, the potential energy comes out to be plus product of the dipole moment and the electric field. This is the maximum potential energy that is experienced by the dipole, and it refers to the unstable equilibrium.